Hello, my name is Monica Biener. I work at the Lawrence Livermore National Lab, and today I would like to talk about bulk nanoporous metals and their use as functional materials and templates. Nanoporous metals made from dealloying have some remarkable properties. These properties are consequences of their bicontinuous nanoporous structure of interconnected pores and ligaments. Nanoporous metals typically have a unimodal pore size distribution, but we can change the length scale of this pore size by a simple thermal annealing treatment. The structure itself doesn't actually change, it's just the scale that it changes. So ligaments and pores are growing at the same time while keeping the shape of the material. We can also make bimodal pore size distribution by starting with different alloys or different dealloying parameters. And that's actually very interesting for applications where we have mass flow through the material. Another very interesting property of the material is that it has a very well-defined crystallinity. So actually the nanoporous material keeps the grain size of the alloy that we start the sample off from. So we have a material that has a length scale of tens of nanometers in ligament size, but also grain sizes, single crystalline grain sizes of several hundred microns or even up to millimeters. How do we make the nanoporous metals? Well, we start with an alloy, basically melting 2 or 3 different metals together, and then we take out the less noble constituent by an etch process, and that can be either by free corrosion or in an electrochemical environment. And that leads to the formation of a lot of vacancies and diffusing atoms, and by a self-organization process we have the formation of this sponge-like very unique structure. And what's very interesting is also that the macroscopic shape of the material is totally preserved. So you can machine actually a piece of the alloy, and the resulting nanoporous material is still preserved in shape. Dealloying is a general process, and it can be applied to many different material systems. We specifically work on nanoporous gold and nanoporous copper. We can make bulk samples, we can make very thin films by sputtering, or we can make extremely thin films by starting with 100 nanometer thick gold silver alloy leaves that you can actually buy in an art supply store. Or we can also apply the process to coating of removable microparticles. Next slide. An additional degree of control is achieved by engineering the surface composition and morphology. And a general approach to do this is actually by atomic layer deposition, ALD, or liquid imbrication followed by freeze drying. ALD is a gas phase-based vapor deposition technique that allows for uniformly coating ultra-high aspect ratio materials with very thin layers. And we have atomic control thickness of the material that allows us to coat materials like nanoporous metals with an aspect ratio of about 1,000 or even higher. And for some applications like catalysis, it is equally important to control the morphology because under-coordinated atoms that you can find at step edges or kink sites are much more reactive than atoms that sit on facets or on regular terrace sites. So it's nice to be able to control what kind of morphology you get at the end. And we have a way to control the morphology by changing the surface diffusivity during the synthesis process. This can be seen in the lower part of the slide. Nanoporous metals have a high surface area, and you can actually think of nanoporous material as three-dimensional arrays of cross-linked nanowires. So the number of surface atoms actually increases with the decreasing diameter of the nanowires. So the smaller you go in feature size, the higher you go in surface area. And surface atoms actually have different properties than bulk atoms because they're missing their neighbors, and thus the electronic density has to redistribute. That's why surface atoms typically have different properties than bulk atoms. And because we are actually working with nanoporous materials that have the pores are all accessible, we can change the properties of those surface atoms by putting them in a different environment. And with this, you can have a surface-dominated tunable bulk material. So one example is the use of nanoporous gold as an actuator. Here we use chemical energy to modify the material in a way that it contracts and expands upon absorption of oxygen. And this is a totally reversible process. We use ozone to absorb oxygen and then CO to abstract the oxygen again. Totally reversible process where you actually transform chemical energy into mechanical energy by changing the dimension of the sample. And with this process we can actually achieve strain amplitudes of about 0.5%, which is comparable to piezoelectric materials. Other applications for nanoporous gold are, for example, catalysis. Nanoporous gold is a very efficient catalyst for partial oxidation of methanol to formaldehyde. The selectivity of nanoporous gold as a catalyst is a result of the fact that nanoporous gold is actually a weak catalyst, so it releases the intermediates before completely oxidizing them, so that makes it very special. Another application for nanoporous gold is the use as a source substrate. Nanoporous gold is a highly active, stable and tunable source substrate that allows for sensing very dilute substances that are Raman active. And finally, nanoporous gold can also be used as a coating for implantable neural electrodes. Nanoporous gold coatings actually maintain the close physical coupling of neurons to the electrode surface, while at the same time reducing the formation of scar tissue. We developed a method to create nanoporous gold libraries on a single chip, and these libraries consist of nanoporous gold patches with different feature sizes that are produced by localized laser heating. And using these nanoporous gold libraries, we're actually able to do parallel studies of cell material interactions to study the structure-property relationship. As we had seen earlier, nanoporous gold is actually intrinsically unstable and is prone to coarsening upon thermal heat treatment. But if we apply a very thin layer of a ceramic material, for example aluminum, by atomic layer deposition, we can completely freeze in this process. Even a sub-nanometer thick coating, or thin coating I should say, of alumina on nanoporous gold completely freezes in the structure and preserves it against thermal coarsening. That's actually very amazing, I think, because you can think of it as a very thin layer of alumina holding a metal core that's been heated up to almost the melting temperature of gold, which is about 1,000 degrees Celsius. We can also apply more functional coating on nanoporous gold, which is titanium, with atomic layer deposition, and with that we can actually increase the reactivity of the material against oxidation of CO to CO2 by a factor of 3, in addition to making the material thermally stable against coarsening. And the interesting thing about the use of nanoporous gold functionalized with TiO2 for pollution control is that this catalyst actually works at room temperature as opposed to other currently available catalysts that work only at elevated temperatures. We can also use nanoporous gold as a structural support and conductive backbone for lithium-ion batteries by coating it with an active material like TiO2. And since we can control the morphology of nanoporous gold very precisely with thermal annealing, and we can control the thickness of the layer very precisely because we're using atomic layer deposition, we have a lot of ways how we can modify the morphology of the material. And by optimizing the material, we can actually increase the power performance of the system in a way that beats all other TiO2-based systems reported in literature. So far I've talked about nanoporous gold and its uses, and also about how we can functionalize it and what we can use the functionalized nanoporous gold for. In a next step, we can actually remove the substrate, the nanoporous gold, and keep the coating as a freestanding material. And that actually makes for a very unique morphology. It's a nanotubular material and we can have a lot of control over the feature size and the thickness of the material. So we're starting with nanoporous gold, apply coatings with atomic layer depositions, and then etch out the core. And what's left is, as you can see in the TEM picture in the center of the slide, what's left behind is the nanotubular, very unique morphology. And we can control, as I said, we can control the density and the feature size of the material very precisely. It turns out that this material, because of its unique morphology, is very robust. It outperforms other materials, aerosol-based materials in the density range by about an order of magnitude in mechanical properties because of its nanotubular structure and its interconnectedness of the ligaments. So what you see here on the left upper corner is the nanoporous template, heat treated at different temperatures. That's why it shows a different color. If you take this template and then coat it with different materials and etch out the core, we have this unique nanotubular material at different feature sizes. And we can easily switch the material that we coated by switching to a different ALD process. The images that you see in the upper line are nanotubular materials for alumina, titanium, and zinc oxide. And what's very nice about this process is actually that the macroscopic shape of the sample is totally preserved. So you can actually machine the material as an alloy piece in a very specific shape, and that shape is then transferred into the foam that's the result of the whole process. And these foams can go down to densities in the single-digit milligram per cc range. So these foams normally are not easily machinable, but you can start with the machining early on for the alloy material and then keep the shape. So that's one advantage of this whole process. And we can nicely control the feature size by preheat treatment of the template, and we can control the density by the number of ALD cycles that we actually apply. Potential applications for this unique nanotubular material include the use of membranes for filtration and gas separation. We're currently also working on using this material for battery membranes. Because of the low density, we can also use it as bright X-ray sources for diagnostics. It has a high surface area, that's why we could think of using it as a sensor or also as an active electrode for photocatalytic applications. The strength of the material really lies in the unique morphology, because you have two independent pore systems that are totally separated by the membrane, but they are interconnected, and that's really a very unique morphology and mimics systems in nature where you have a very efficient mass transport. So we can use it as a three-dimensional membrane because this ALD coating has some nanoporous where we can actually transport material through. So it's a three-dimensional membrane with interconnected pores. That's what's making it so unique. Thanks for your attention, and if you have any questions, please contact Anne-Marie Meike in the Industrial Partnerships Office.